It will soon be of use to us to have a numerical summary of the distribution of a random variable without needing to know the entire distribution itself. And that's exactly what the expectation gives us. The expectation of a random variable is the weighted average of the values that that random variable takes on, where the weights are the probabilities of those values. So we denote the expectation with E of x, expectation of x, and the most common way of expressing the expectation is a sum over all possible values of x. And so we sum over all possible values little x of x, so value, times p x equals x. And so this is the probability of the value little x. So this is a sum of value times probability of value. An equivalent way of expressing the expectation is as a sum over all possible samples instead of all possible values. So we can sum over all possible samples s, x of s, which is the output of the random variable x for the sample s, times the probability of seeing the sample s. So the second definition uses the fact that random variables themselves are functions of samples. Now these two formulations are equivalent, but for the most part we will stick with this first formulation just because it makes doing computation much easier. So there are a couple things we need to talk about with regards to interpreting expectations before we do any calculations. The most important thing to note is that the expectation of a random variable is a number. It's not another random variable. So given a random variable, its expectation is a number. It is a fixed quantity. There's no randomness to it. It is analogous to the average. Okay, and so one of the properties it shares with the average is that it has the same units as the random variable itself. And so, for example, if our random variable is the number of pips we see on a roll of a die, the expectation will also be some number of pips on a roll of a die. But one thing to note with the expectation is that it doesn't need to be a possible value that the random variable can take on. So an exercise for you to work on right now is what is the expectation of the number of pips we see on a roll of a die? And is it 1, 2, 3, 4, 5, or 6? The hint I'll give to you is that it's not, but that's an exercise for you to work on. Let's look at a concrete example of computing the expectation of a random variable. So over here on the left, we have a familiar example. It's this random variable x that takes on four possible values, 3, 4, 6, and 8, with the probabilities 0.1, 0.2, 0.4, and 0.3. And so the definition of the expectation of x is this weighted sum of value times the probability of that value. And so you can see here, we have the first value, 3, multiplied by its probability, which is 0.1, plus the second value, which is 4, times its probability, which is 0.2, plus the third value, 6, multiplied by its probability, 0.4, plus the fourth value, 8, multiplied by its probability, 0.3. So you can see we've gone 3 times 0.1, plus 4 times 0.2, plus 6 times 0.4, plus 8 times 0.3. And if you simplify and do the addition, the result you get is 5.9. And so the expectation of this random variable is 5.9. One thing to note is that 5.9 isn't one of the possible values that this random variable takes on, right? The possible values it takes on are 3, 4, 6, and 8, and 5.9 is not one of those. So the expectation does not need to be one of the values that the random variable takes on. Another way to interpret expectation is as the balance point or center of gravity of the distribution histogram of a random variable. And if we use this fact, in a lot of cases we can compute expectation without actually having to do any calculation. For example, let's suppose x is uniform on the set 1, 2, 3, 4, so on and so forth through n. In this case, the expectation is n plus 1 divided by 2. For example here, a standard die takes on the values 1, 2, 3, 4, 5, and 6, all with the same chance, right? The probability of seeing 1 dot or 2 dots, so on and so forth, are all 1/6. Here, 3.5 is in the middle. It's the balance point of this distribution histogram because each of these events is equally likely. If the die wasn't uniform across these numbers, then it's not guaranteed that the expectation would be exactly in the middle. But since it is uniform, the expectation is in the middle of 3 and 4, which gives 3.5. And more generally, this is n plus 1 divided by 2. Another example is when our random variable is uniform on the interval 0, 1. And so what this means is our random variable can be any real number between 0 and 1, and each of those real numbers is equally likely. In that case, the balance point or center of gravity is exactly in the middle of the interval because each of the values is equally likely. The balance point is exactly in the middle, which is 0.5. And again, if it wasn't true that all of the values were equally likely, then the balance point isn't guaranteed to be in the middle. But since everything's equally likely, balance point is in the middle. Lastly, we can look at the normal or Gaussian distribution with parameters mu, which is the mean, and sigma squared, which is the variance. For the normal distribution, the expectation is defined to be this parameter mu, but we can see that from the distribution picture, right? The center of gravity here is exactly where mu is. We will now start looking at functions of random variables and how these functions play with the expectation of our random variable. Let's suppose x is a random variable, as we've been doing, and let's say a and b are some real number constants. Okay, so these are some fixed values. Ax plus b is a new random variable, and we call it a linear transformation of the random variable x. A property that the expectation satisfies is that the expectation of ax plus b is equal to a times the expectation of x plus b. And so we will sometimes refer to this as the linear transformation property of expectation. This will be very useful to us in the future when we look at linear transformations of random variables and how those play with the expectation. And one example of that is when we look at, the sample mean versus the sample sum. The sample mean is a linear transformation of the sample sum, and this is something we will see later in the lecture. So the expectation of ax plus b is equal to a times the expectation of x plus b. Now, more generally, the expectation of some function g of x, where g is any function, is equal to this weighted sum of g of x times the probability that x is equal to x. Now you can see here this resembles very closely the formula for the normal expectation, but we replaced capital X with g of capital X, and we replaced little x with g of little x. And so this formula tells us how to compute the expectation of some function of our random variable. As an example, let's suppose again that x is uniform on the set 1, 2, 3, 4, 5, 6, and so it's a standard die. The expectation of the square of x, so the expectation of x squared, is this sum of x squared times the probability that x is equal to x. So the expectation of x, there would not be a square here, but since it's the expectation of x squared, we square the values before weighting them by their probabilities. So the expectation of x squared is 1 squared times 1/6 plus 2 squared times 1/6 plus 3 squared times 1/6, and so on and so forth. And that ends up being 91/6. This specific calculation, that of the expectation of x squared, will be something that we do commonly to compute the variance of a random variable, which is something that we will look at momentarily. One thing I wanted to point your attention to is that the expectation we just computed, the expectation of the square of x, is 91/6, which is 15 and some change. But the square of the expectation of x is 3.5 squared, which is 12 and some change. And we got this 3.5 from a couple slides ago. Remember where? That's the middle of these 6 values. And so since 15 and 12 are different numbers, it is not true that the expectation of the square of x and the square of the expectation of x are the same thing. These are different. And more generally, the expectation of a function of a random variable is not the same as that function applied to the expectation of the random variable. It's true when our function is linear, but in general, it is not true. Another property that expectation satisfies is that for any two random variables x and y, the expectation of their sum is equal to the sum of their expectations, regardless of the relationship between x and y. You can actually generalize this to any number of random variables, not just 2. And so more generally, the expectation of a sum is equal to a sum of expectations. We're not going to prove this fact in this class, but the proof is relatively straightforward if you use the second definition of expectation that we presented, the one where you sum over all possible samples S. One example use case of the additivity of expectation, which is what we call this property, is with the sample sum. So pretend we have a collection of random variables x1, x2, so on and so forth through x sub n, where all of them have the same expectation mu. The sample sum then is just the sum of all of our n random variables. And the expectation of the sample sum, then by the additivity of expectation, is the sum of all of the individual expectations. And so the expectation of the sum is a sum of expectations. And now each of these individual expectations is equal to the value mu. We are adding mu to itself n times, and so the expectation of the sample sum is n times mu. And results like these we will use quite often, especially towards the end of this lecture. You can actually bundle the linear transformations property and the additivity property into a single statement called the linearity of expectation, which actually applies to not just 2, but to any number of random variables, regardless of their relationship. This is not a term that we will use that often in this class, but it's something that may come up, and it's something that you should be aware of, the linearity of expectation. We will wrap up this video by looking at the expectations of the Bernoulli and binomial distributions that we looked at earlier. So if you recall, if x follows the Bernoulli distribution with parameter p, then the probability that x is 1 is p, and the probability that x is 0 is 1 minus p. The expectation of x then is a weighted sum of value times probability of value plus value times probability of value. Here, the two values are 1 and 0, and their probabilities are p and 1 minus p. And so the sum of 1 times p plus 0 times 1 minus p is just p. And so a nice property of Bernoulli random variables is that their parameter is both the probability that that random variable is equal to 1, and it's also equal to its expectation. So that's the Bernoulli distribution. Let's look at the expectation of the binomial distribution. So recall, we can think of the binomial distribution with parameters n and p as the number of successes in n independent trials of some event, each of which occur with probability p. Well, we know that one trial of an event can be modeled with a Bernoulli random variable with parameter p. So we can think of our binomial random variable with parameters n and p as a sum of n individual Bernoulli random variables, each of which has the parameter p. So we can write x, our binomial random variable, as I1 plus I2 plus I3 plus so on and so forth plus I sub n, where each I sub j is an indicator indicating success on the trial j. So I sub j is equal to 1 if trial j is a success, and I sub j is equal to 0 if trial j is not a success. And so you can see x is equal to the sum of 1s and 0s, and as a result, x is equal to some number between 0 and n, indicating the number of successes. We know from the last slide that the expectation of a Bernoulli random variable is its parameter, p, and so the expectation of I sub j is equal to p. Since our random variable x is a sum of n Bernoulli random variables, each of which has the mean of p, we know by the additivity of expectation, the expectation of x is the expectation of this sum, which is a sum of each of these individual expectations, each of which is p, and so the expectation of x is equal to n times p. And so the expectation of the binomial random variable with parameters n and p is n times p. As a real-world example, suppose we flip a fair coin 10 times, then the number of heads we see follows the binomial distribution with n being equal to 10 and P being equal to 1/2. And using this formula, the expectation is 10 times 1/2, which is 5, which matches what we would think, right? If you flip a fair coin 10 times, you would expect to see 5 heads and thus 5 tails.